In this video, we're going to talk about half-life. Here's the definition: the time required for the concentration of a reactant to decrease to half of the initial concentration. Half-life is symbolized with T with the subscript 1/2. Here's the definition again. It is a nice way to talk about how fast or slow a reaction occurs. It's also very common with radioactive elements. So you'll see that a lot in these examples and practice problems. Here are the different half-life formulas. Okay, the only one that's on your formula sheet and the only one that you're going to need to use is the first order one. The other two have concentration of A, which is our generic reactant here. So they're really not helpful because you have to know the concentration of A at any time to figure out the half-life. But if it's a first order reaction, there is no dependence on concentration. So that is one that you will use, and you will see it on your formula sheet. If you have a graph of concentration versus time, okay, what you can do is figure out the half-life that way. Just pick two concentration points. So here it says 0.04 and 0.02. So two concentration points that are half. And then our 0.04 is right here on the graph. Our 0.02 is right here on the graph. So to figure out how much the half-life is, you just look at how much time that took for it to decrease by half. Okay? It was 24 minutes. If you picked another set, so for example, 0.03 and then 0.015, because that's half of that, that's also 24 minutes. Okay, so you can see that no matter what half concentration you pick, you come out to the same half-life. What is the rate constant? Because remember, our formula from your formula sheet has rate constant in it. There's K. Of a first order reaction in which the half-life is 3 hours. So you use your half-life formula. Manipulate it for K. And then we'll plug in the 3 right here. So that means K is going to be this, which is right here. What fraction of a reactant remains after 3 half-lives of a first order reaction? This you don't actually even need to know its first order because we're not going to use the formula at all. Okay, so let's say we start with 1 because that's our full amount, 1, or a lot of these will say percents, so it would be 100%. And then, so that's at 0 half-lives. At 1 half-life, we would expect this to be 1/2. At 2 half-lives, we would expect it to be 1/4. And at 3 half-lives, we would expect it to be 1/8. So the answer here is 1/8. And that's just, again, taking it, starting with 1 and dividing it by 2 for each half-life that passes. So here's a percent one. 93.75% of some radioactive isotope has decayed after 8 hours. What is the half-life of this isotope? So the best way to figure this out is to figure out how many half-lives have passed. So if we do the same thing we did on the last slide, but with 100 this time, okay, we're going to want to figure out how long it takes to get down to 6.25%, because that's how much is left, right? This says 93.75 has decayed, so 6.25% is left. So this will be 0 half-lives. If we take half of that, this will be 1 half-life. Then we go to 25. That's going to be 2 of them. 12.5, 3. 6.25, 4 half-lives. Okay, so we know that 4 half-lives have passed. If 4 half-lives are 8 hours, that means each half-life is 2 hours. So that's the answer here. So here, the decay of an iodine isotope, you'll hear isotope a lot in these because they're radioactive, has a half-life of 10 days. After 40 days, there is 1.5 grams of that iodine isotope present. What was the original mass? So we're going to do the same thing, except go backwards. So we know that we had 1.5 after 4 half-lives. We're going to go back, because 40 days is 4 half-lives, and we want to figure out what it is at 0. So instead of dividing by 2, which is what we've done before, we're going to multiply. So here, it would have been 3. Here, 6, 12, and it would have started out as 24. So that's our answer. If an 84-gram sample of thorium decays with a 10-minute half-life, how much would the sample weigh in a half hour? So at 0, it's 84. 10 minutes is going to be 1 half-life. 20 minutes will be 2 half-lives. 30 minutes will be 3 half-lives. So after 1, it will be 42 grams. After 2, it will be 21 grams. And after 3, it will be 10.5 grams remaining. So that's how much the sample would weigh after 3 half-lives or 30 minutes. Last one for this video. A sample of ancient grass mat containing radioactive carbon half-life is 5,730 years. Seems to be admitting 6.25% of the radiation that a sample of a grass mat woven last year would have had. How old is the ancient grass mat? So we are going to do the same basic idea. Here we have 6.25%. This might be something you start to get the hang of with the percents. So at 0 half-lives, we have 100. At 1, we have 50, and we've done this before. We have 25 at 2 half-lives. We have 12.5 left at 3 half-lives. And we have 6.25 left at 4 half-lives. Okay, and that, again, because we do percent so often with half-lives, you might have already known that. 6.25% left means 4 half-lives. So 4 half-lives times this many days, which is our half-life, gives us not days. I'm like, that doesn't make any sense to me. Years, sorry. Gives us this many years. So this is how old the ancient grass mat is. And that's it for half-life. That's basically the whole gist of it. Last part of this is to sketch the energy diagram. Now, we haven't done thermo yet, but I will tell you that you might know from honors that this is going to be an endothermic, which means it will start, well, excuse me, it will end higher than it started. Okay, so that's where it's going to end. You have two steps here, and the first step is the slow step, so it's going to have the higher bump. So we're going to have two bumps, and the second one's going to be a little bit lower, and then we end higher because it's endothermic.